Okay, good morning. Can you hear me? Boleh dengar? Okay, anyone? Boleh dengar ke?
Dengar saya.
Okay, thank you. Okay, good morning. Today we will continue with the lecture. Okay, on chapter 6, part 1. So we are currently studying about the energy and also energy analysis. Okay, that we will see in this chapter. Okay, so previously we have seen the basics of energy. So what is energy about, and also energy transfer by heat. Okay, so today we will continue with the second part, which is the work. Okay, the energy transfer by work. If energy crosses boundary is not heat, okay, due to temperature difference, then it is a work. Okay, so kita kena tahu kalau energy transfer tu kena melalui boundary. Boundary of the system. Kalau dalam system, so it's not considered as energy transfer. Okay, so if the energy transfer crosses the boundary, kalau yang itu bukan heat, so heat dia berkaitan dengan temperature difference. So ada perubahan temperature. Okay, so if not because of temperature difference, then kita consider it as a work. Okay, kerja. Okay, so more specifically, work is the energy transfer associated with the force acting through a distance. Because we know formula work equals to force times distance. Okay, force times distance. So work is the energy transfer with the force through a distance. So meaning you need to move a distance. Okay, a distance of d. Okay, then we can relate it with W equals to F times D. Okay, so normally the unit that we will use is Newton meter or Joule. Okay, ataupun selalunya dalam SI adalah kilojoule. Okay, so example of energy transfer by work is the rising piston. Okay, piston yang bergerak. Okay, and also rotating shaft. Okay, current carrying wire. So even current analysis pun berkaitan dengan work because there's a force or power, electrical power moving through a distance, current moving in a distance. So it is considered like a work. Okay, work done per unit mass. Saya pernah beritahu, kalau per unit mass maksudnya kena bagi dengan mass, bagi dengan kilogram. Okay, then W dia jadi kecil. So W besar adalah work done. So W kecil adalah work done per unit mass. Okay, so the unit is kilojoule per kg. Okay, rate, if the word rate is there, so meaning it is related to power or over time. Okay, per saat ataupun per minit, per jam. Okay, that is what we call as a power. Okay, can see the picture here. So work done by a system, 30 kilojoule of work. So meaning the W, capital W equals to 30 kilojoule. So mass, let's say 2 kg and time is 5 seconds. If got dot, meaning is power. So W with dot, so meaning it's a power or rate of doing work. So 30 divided by 5 equals to 6 kilowatt. So the unit is kilowatt. And W kecil, okay, small w is work done per unit mass. So work done per unit mass, work done bagi dengan mass, which is 2 kg. So 30 bagi 2, so dapat 15 kilojoule per kg. So unit is kilojoule per kg. Okay, so energy transported by heat and work and the classic sign convention. Okay, so energy may cross the boundary of a closed system only by heat or work. Okay, closed system adalah control mass. So meaning the heat is only transferred through heat or work. Yeah. Okay, so energy transfer across the system boundary due to the temperature different. Ini kita dah tahu. Kalau ada temperature different, it is heat. If other than that, uh, especially if extended to lift a weight. Lift a weight maksudnya dia berkaitan dengan force and also distance. Yang itu kita panggil as work. Okay, heat and work are energy transport mechanism between a system and surrounding. Okay, so similarity between heat and work. Boleh tengok dekat sini, both are recognized as a at the boundary of the system as they cross the boundary. They are both boundary phenomena. So meaning, for energy transported by heat and work, you need to cross the boundary. Kalau di dalam, it's not considered as energy transfer. System possesses or releases energy. Possesses maksudnya dapat. When there's a cross of energy, so either the system dapat energy or it releases energy. So either one. Okay, both associated with the process, not the state. So meaning is something that is happening along the way. So dia bukan satu keadaan. Satu, keadaan dua, tak. So it is a process, meaning it's a movement from state to state, state 1 to state 2, in between. Okay, so it's a part function. So sebab yang itu adalah proses. Okay, so you can see here the following figure illustrate the properties. So ni adalah PV graph, pressure times volume. Okay, so PV graph. So dalam ni dia ada a lot of information lah. Okay, point function and depends on only on the state and not on how the system reaches the state. So boleh tengok, you have state 1 and also state 2. So there are two processes, process A and also process B. So if the transfer, energy transfer from 1 to 2 is through process A, kalau melalui process A, so you can see, so VA is 3, 5 tolak 2. Okay, and work done is 8 kilojoule. Kalau melalui proses ni, dia 12 kilojoule. So there are two different processes. So in order to reach from point 1 to point 2, you boleh ada berapa banyak proses. So you can have process A, B, C, D, E. So and as many as processes as you want, but output dia sama. Cuma proses ni you tengok work done is different. So heat and work are part function. Thus, that is the magnitude depends on the part flow. So depends lah. Kalau you gunakan jalan yang panjang, meaning the magnitude will be different. Even though the differences in the volume are the same, tapi magnitude adalah berkaitan dengan part yang you laluan yang mana you nak ambil. So maybe if part C, so maybe it goes like this. So it goes like this. So meaning the work done can be 20 kilojoule. So depends. So depends on the part. Sama macam kita nak bergerak dari satu point ke satu point, katakan dari Arau nak pergi ke Kanga. So there are various routes that you can take. So depends on the route yang you ambil. So the time will be different. So maybe kalau you ambil highway Changlun Kuala Perlis, you boleh sampai dalam 10 minit. So if you follow jalan melalui Jejawi, so maybe it will take 20 minutes. So depends. Tapi destinasi dia sama. Okay, so that is what it is explaining through this. Okay, so heat and work are directional quantity. So directional maksudnya is a vector. Okay, vector because it is having a magnitude and also direction. Okay, so magnitude and also direction. So dia ada sign convention. Sign convention maksudnya dia ada apa? Symbol. So either it's a positive or negative. Oh, there's a correction. Sebab waktu I go through this slide, so there's a correction. So correction I have done in the red color. So tukar, so tolong tukar yang ni. Okay. Okay, so I explain first. Okay, if the heat transfer to a system, okay, to a system and work done on the system are positive. Okay, so later I explain lah. Okay, heat transfer from a system and work done by the system. So ada dua term, done on and done by. So yang ni dalam description tadi dah terbalik. Okay, so terbalik. So tolong betulkan. Okay, so please correct it. So generally, if the system is getting energy from outside, so it can be in the form of heat or it can be in a form of work. So sign dia akan jadi positif. So gambar ni pun actually dia silap lah sebab sign ni. Okay, so work because the work because symbol turbine ni actually, from my understanding, the work is done from outside, that's why the turbine ni pusing. Tapi berdasarkan gambar ni, so steam is moving the turbine or the propeller. So it's okay lah, just tolong abaikan gambar ni. So kita ada example lain at the back. Okay, we have other example at the back, so just ignore this picture. Okay, but from this picture we know that work done. Okay, so heat is transfer. So when you are giving heat, the system will get dia akan dapat, so it will get a new heat, so it will be added, and the work done from outside to inside, so energy is added. Okay, so you either can put you can write it in the form of symbols or signs, positive or negative, ataupun you boleh tulis in and out. So like here, so if the heat is entering the system, so heat is a Q, so Q in maksudnya dia masuk. Okay, Q out meaning is going out. Okay, so work in masuk, W in, so W out maksudnya work is going up. Okay, so when ini tak apalah. So if the interaction is not known, we simply assume a direction of interaction, subscript in or out. So tulis macam ni lah. Okay, so another form macam I bagi tahu tadi. So there's another form of energy transfer, also similar in the electrical work, where the current is moving from one distance to another. Okay, so the rate of electrical work done by electron crossing a system boundary is called electrical power and is given by the product of the voltage drop. So power, electrical power, kita tahu the formula for power adalah P equals to VI. Okay, so I selalu ingatkan, okay, power is very important. So VI, very important. Okay, power is very important. So electrical power is actually electrical work done by the electrons. Okay, so power, so meaning W ada dot. Okay, there's a dot on top, so indicating is a power, and the unit is watt. Okay, the amount of electrical work done in a time period is found by integrating the rate of electrical work over time. Yang ni adalah over time. So from time 1 to time 2, so there's a calculation. Okay, so this is generally the formula to calculate the electrical power. Okay, so then we also have a mechanical form of work. Okay, dari pergerakan ataupun movement of something, so we'll consider it as a mechanical. So there are various form of energy transfer. Okay, so it can be transferred through heat, it can transfer through work. Work pun ada banyak. Okay, ada banyak. So earlier we see the electrical. So now we are seeing the mechanical form of energy transfer or work. So work is energy expended by a force through a distance. Okay, so thermodynamic work is defined as energy in transition across a system boundary and is done by a system if the sole effect external to the boundary could have been the raising of it. Okay, so as I say, so work is berkaitan dengan force times distance. Okay, work is force times distance. So thermodynamic work, so yang bagi tahu dekat sini, sole effect adalah raising of weight. So you angkat something, so a weight is moving from one point to another point over a distance. So raising of the weight ataupun you angkat. Kalau you angkat ada ketinggian. So that means there's a raising of weight. So then you can consider it as a thermodynamic work. Okay, the work done by a constant force F on a body displays a distance S. So ni adalah formula dia. So W equals to Fs. So the unit is kilojoule. If the force is not constant, so meaning it's changing over time from time 1 to time 2, you boleh gunakan form ni. Yang ni kalau constant, yang ni kalau tak constant. Okay, so there's a changing between point 1 to point 2. Okay, so common type of mechanical work energy. So mechanical work energy actually got a lot. So dekat sini listed. So it can be a shaft. Shaft macam dalam kereta. Ada shaft kan? Car, the wheel shaft. So meaning is a rotating. So shaft normally will be with a rotation. Okay, rotation. So force dalam rotation adalah torque. Okay, then we also have a spring work. Okay, movement of a spring. So meaning the elongation of spring. So either you compress the spring ataupun you panjangkan. So you expand, elongate the spring. Okay, so work done by of elastic solid bar. Okay, so anything that is you moving atau you move a box or you moving a rock or something yang solid. Okay, so work associated with the stretching of a liquid film. So you have a film ataupun you ada gel, so you tarik, you stretch ataupun compress. So it is also associated with work. So work done to raise or accelerate a body. So meaning you tekan minyak, so kereta you bergerak dengan lagi cepat. So it is considered as a work done because it involve a force and also there's a distance change. So boleh consider. So these are some of the mechanical work transfer, okay, of energy. So there are two requirements. So dua syarat. Okay. First, there must be a force acting on the boundary. Macam I bagi tahu tadi, dia kena melalui boundary. So if within the system is not considered as a work. So the work must cross the boundary. So if it didn't cross the boundary, it's not considered as a work. Okay, and the boundary must move. The boundary must either expand or compress or must move from one point to another point. So that are the two requirements of the work. Okay, so we will see few mechanical work, few of this. Okay, so kita tengok dulu shaft work. Okay, so this is something related with movement in rotation. Okay, so a force F acting through a moment arm with a radius R. Okay, so ini adalah formula for torque. So T adalah torque. So T is torque. Torque equals to force times radius. Force times radius. So you have a force. Okay, so force and a radius. Then you will, when the force is moving in a radius, so the torque will be generated. The torque is actually force in a rotation. Okay, so these are the formula. So from derived from here, F equals to P over R. Okay, this force act through a distance. So if you are moving through a distance, so S equals to 2 pi R. Okay, 2 pi R is the lilitan kan, lilitan bulatan. Okay, so over N. So how many time it rotate? Okay, so you replace it in this formula. So you will get, so work SH adalah shaft. Okay, SH is shaft. Work done by a shaft or shaft work equals to Fs. So you replace it here. So F is T over R and S is 2 pi Rn. Okay, so you simplify, you remove the R. So you get work, work, work done by a shaft equals to 2 pi Nt. Okay. So this is the work done and the power through a time per unit time. So you just take this. So work done by a shaft dot equals to 2 pi. So the only thing that you can relate with time is the rotation. Okay. So n number of rotation. Okay. N dot times 50 and the unit is kilowatt. Okay. So some of the example is the boat. Okay, so you have an engine. So engine is associated with the propeller. When the propeller move, so it will take a force from the water and the boat move forward. Okay, so if you increase, you press more on the pedal, so it will move faster. Okay, so this is associated with the shaft work. Okay, so you can see the example. Okay, determine the work transmitted through the shaft of a car when the torque applied is 200 Newton meter. So torque T equals to 200 Newton meter and the shaft rotates at the rate of 4000 revolution per minute. So 4000 RPM. Okay, so the formula. Okay, so it has to determine. So either the question will ask you to find the work or work done, work or the power. Okay, the shaft power. Okay, or the shaft work done per unit time. Okay, so here it has to determine the power transmitted through a shaft. So meaning you need to find the shaft power. Okay, so WSH dot equals to 2 pi n dot T. So this is the formula from the derivation earlier. So 2 pi, so n dot is 4000 revolution per minute. Okay, so you can write like this. And the torque, torque is 200 Newton meter. Okay, so you have two unit conversions. So you simplify this. At the end, the power transmitter is 83.8 kilowatt. Okay, so this is a solution for this. Okay, so go through again the example so that you will get a better understanding. Okay, so the shaft work is the first mechanical work. So we will see one more. So which is the spring? Okay, spring we know is either can compress or it will extend. And normally without any force, the spring will have a rest position. So meaning no compression, no elongation. So this is a normal length. So if you apply a force, then the spring will elongate. Dia akan jadi panjang. So yang ni adalah the rest position. Okay, so meaning waktu you beli spring tu pun, spring tu ada dalam position ni. Well, only when you apply force, it will increase. Okay, so this is you can see here. For spring, the work is F equals to Kx. So K is the spring constant. Okay, and the unit for the force is kilonewton. And the spring constant, the unit adalah Kn per meter. So normally in the question, the spring constant will be given. Okay, so that you can use for the calculation. And so this is the formula for the work done in a spring. So W spring equals to half K x2 square minus x1 square. Okay, that's a derivation for this. So x1 adalah initial displacement. So final minus initial. Okay, so you can see here. So this is the rest position and this is the elongation. Okay, dx. Okay, so you can see here if you apply F1, force 1 equals to 300 Newton. Okay, and F2 is 600 Newton. So the movement of the distance x1 equals to 1 millimeter and x2 is 2 millimeter because the force is increased by double. Okay, so we understand that the elongation also will be double. Okay, so you can see an example. So how it is used. Okay, how much work in kilojoule can a spring whose spring constant is 3 kilonewton per cm? Okay, kilonewton per cm. Okay, sorry, not cm. Okay, betul. So you see here 3 kilonewton per cm. So you cannot take this here because here you need to use kilonewton per meter. Okay, so you convert this to 300 kilonewton per meter. Okay, so before you use in your equation, you need to convert it to the proper unit. Okay, so it only asks to find the work because here you have two formula. Um, okay, one is F equals to kx and also uh, this formula, the work done. Okay, so no for the power, so no power. Okay, so W equals to so this formula. So this is the derivation. How you can get this? Okay, so from 1 to 2, so you can take from this formula. So W equals to F ds from 1 to 2. So F is equals to Kx for the spring. So Kx dx. So K is a constant. So you take it out. So you just integrate this. So when you integrate this, you will get this formula. So half K x2 square minus x1 square. Okay, the question is saying produce after it has been compressed. So the question can be compression or elongation. Okay, from its unloaded length. So unloaded length maksudnya length adalah kosong. Okay, so you replace the value. So 3 kilonewton per cm. So kali dengan 100 lah. So 300 kilonewton per meter. So bagi 2. So you apply in this formula. So 300 kilonewton per meter divided by 2. Okay, so x2 square is 3 cm. So 3 cm is 0.03 meter square. Okay, minus. So unloaded length adalah kosong. So kosong square. So you solve this, you get 0.135 kilonewton meter. But the question it asks you to give in kilojoule. So you times with the unit conversion. So cancel. So you will get this formula. So 0.135 kilojoule. Okay, so this is how you calculate for the spring. Okay, so first law of thermodynamic. Okay, we'll see some of it. Okay, so first law of thermodynamic is known as the conservation of energy principle. Okay, conservation of energy. Okay, so we know that conservation of energy principle saying that energy cannot be created or destroyed, you only can change from. So you can see the example here. Okay, so you have a rock on the cliff. Okay, for when the rock is suspended over height. Kalau satu benda tu kita letak dekat satu height and it is on the verge of falling down but it is stopping. Macam ni batu ni dia nak jatuh tapi it is stopping at one point. So the ketinggian dia adalah Z. So the height is Z. Okay, so at this point, so the potential energy equals to 10 kilojoule. So let's say it's a 10 kilojoule. So no kinetic energy because no movement. Okay, so the velocity is zero. So kinetic energy becomes zero. Okay, so once the rock falls from the cliff, so over time, the potential energy reduce because no more at rest. So it's already in the moving. So it will be slowly reduced. So at this point, so the potential energy from 10 becomes 7 and the kinetic energy from 0 become 3. But the total energy is still 10. So that's why it says that the first law of thermodynamics says that so energy cannot be created or destroyed. So the total energy cannot be from 10 become 12. So it need to receive some form of energy from elsewhere, or it need to be converted. So the total still the same 10. Okay, so the Joules experiment lead to a conclusion. So there's an experiment called a Joules experiment. So you can go to YouTube to see how Joules experiment is conducted. So from Joules experiment, we can conclude that for all adiabatic process between two specific states of a closed system, the net work done is the same regardless of the nature of the closed system and the details of the process. So adiabatic process meaning no heat transfer, only got work. Okay, work can cross the boundary but no heat transfer. So that is what we call as a adiabatic process. So in a adiabatic situation, in a closed system, so meaning control mesh, so the net work done is the same. Okay, so in the system, it will be the same. Okay, so that is what we call as a fundamental principle of first law. So meaning the major consequences of the first law is the existing of and the definition of total energy. So total energy, like here we can see the total energy is 10, uh, and here also the 10 the same. So the consequences maksudnya so hasil dia. Okay, hasil from first law adalah a new term called total energy. Total energy, so we are considering the total energy of the system, which is 10. Okay, so considering that the network is the same for all adiabatic process, so based from Joules example, Joules experiment, so we can read here. So from here, we know that the network is the same for adiabatic process. So kalau soalan tu bagi tahu is a adiabatic process, you need to know that the network throughout the system will be the same. Okay, so two specific state, the value of the network must depend on the end state. So in this case, so we only take the network at the end state. Because it represent the total energy. So contoh dia, so macam tadi, example tadi. So initial state, so potential energy equals to 10 kilojoule and kinetic energy equals to 0 kilojoule. And final state, potential energy is 3 kilojoule and kinetic energy equals to 7 kilojoule. So for your analysis, you only take this value because it's still the same. Okay, it's still the same because it possesses the same total energy. Okay, so you simply state that the changes in the total energy during the adiabatic process must be equals to the work done. Okay, so because the Q equals to 0, so the only work, only energy transfer is through work. Okay, so you can see here the increase of the energy in the potato. So that's a symbol. So this triangle of E, so meaning the changes in E. So if the potato, you are eating up the potato, so from outside the heat is entering. So let's say the Q in or the heat transfer in equals to 5 kilojoule. So for your analysis, you're only taking into consideration the changes in the energy. So energy yang ada dalam ni you disregard because it's the same. So you only consider in your equation. So changes of E equals to 5 kilojoule. It changes in energy either decrease. So let's say the heat is going out. So Q out equals to minus 5 kilojoule, meaning the changes in energy is minus 5 kilojoule. So same for electrical. So let's say the work in is 5 kilojoule. So the changes of energy in the system is 5 kilojoule. So you need to consider the changes of the energy. Okay, so you can see here also some of the okay. So I think this is something important. So please pay attention here. Okay, so you can see. So that's a system. Okay, so let's say this is your stove, or you are trying to eating up something. Okay, and you are getting the heat from outside. Okay, so let's say the Q in. So the arrow is going in. So Q out, arrow is going out. The Q in equals to 15 kilojoule and Q out is 3 kilojoule. Okay, so the changes of the energy inside is total Q net. Q net is Q in minus Q out. So Q in minus Q out. So we will see this in part 2. Okay, chapter 6, part 2. So you will see the formula to calculate the energy. Okay, so Q net here is Q in minus Q out. So 15 minus 3 equals to 12. Okay, so in a adiabatic system, okay, adiabatic system, so this is, so the turbine is inside. So that's a rotation here. So the work, shaft work done in, so meaning the system, it is a W in. So W in equals to 8 kilojoule and also no heat transfer. Okay, so meaning the changes in energy is from the work done, so which is 8 kilojoule. So if this is a WSH out, meaning WSH out is work done by the system, so meaning the energy is released from the system, so it can be minus 8 kg. Okay, and one more. Okay, so work done by the system is on the system meaning work W in. W in is 10 kilojoule. So the changes of energy in the system is 10 kg because energy from outside is entering. So meaning the energy is positive inside the system. Okay, so this example is more complex and easier to understand. So the energy change of a system during a process is equal to the net work and heat transfer between the system and its surrounding. Okay, so if this in this case you have both. So because this is not a diabetic system, if a diabetic system, only work done is considered, no heat transfer. Okay, but this case, so this is a normal closed system. So the we can see the heat is transfer in Q in. Q in is heat transfer in. So Q in equals to 15 kilojoule, and heat is transferred out. Q out equals to 3 kJ, and work is done on the system. So W in. So W in is 6 kilojoule. Okay, so the total energy change. Total energy change is, so Q in minus Q out. Okay, that is the net Q. Okay, plus 6. So 15 minus 3 plus 6. So you get 18 kilojoule. Okay, so this is how you can calculate the changes of the energy in the system. Okay, so that's about it. Okay, so end of chapter 6, part 1. Okay, on Wednesday we covered part 1. So today we cover part 1, 2. Okay, so So any question? So any question so far? Anything that you want to ask? Okay, so if no questions, I think that's about it. So I will upload this video in your Google Classroom, and also I will upload chapter 6 part 2, so that you can get a better picture of the chapter 6, and we will discuss chapter 6 part 2 on Wednesday's class. Okay, so thank you. We will finish early.
Thank you, sir.
Okay.